So I wanted to make this video about dependent t-tests, or deriving an asymptotic approximation to a dependent t-test. I feel like most of my videos so far have been about independent variables, and so I wanted to take a trip back to the world of dependent variables. And so we'll be deriving this approximation to the dependent t-test, and then I'll be using R to simulate side by side our approximation versus the actual test itself. So, a initial question, what exactly is a dependent test anyways? Dependent tests are used in longitudinal designs, which is kind of like a sequential design. So for example, say you have a group of students and you measure, actually I have this example here. So you're observing test scores of a group of students, and it's one group of students. And then after you have them take this test, you introduce some type of intervention. In my toy example, I have them eat spicy food and then take the test again, or take a similar test or whatever, however the design is. And then you measure if there are any effects before and after this intervention. And so this is a dependent test because you're using the exact same group of people, or the exact same group of, whatever the case is. Contrary to independent tests where you would have two completely different groups, i.e. independent. And so the main concern with the dependent tests versus independent is that if you try to use a independent approach or an independent test to a design that is dependent, then your variance estimates will be a little weird because they do not account for the correlation. So when you have these dependent groups, these groups will be correlated because they are the exact same group, versus if you have two completely separate groups, then since they are independent, they will not be correlated, or at least theoretically they won't be correlated. And so when you have this correlation between these groups, if you don't account for this correlation, then your variance is going to be overestimated, which can lead to type 2 errors, which is this last bullet point that I forgot I wrote, but this is essentially stating what I just said. So now we'll get into the math, which will be the biggest portion of this video. So I have two groups, x and y, and x follows some arbitrary normal distribution with mean mu x and standard deviation sigma x, and this is my parametric distribution for group 1. And then likewise I have my y group with mu y and sigma y, and this is my parametric distribution for group 2. However, in this case, since this is a dependent design, y is our dependent group, and the dependency here is this, the location parameter mu y is actually dependent on the distribution of x. And so mu y, I'm saying, has a distribution, another normal distribution with mu x and sigma x, because our distribution y is completely determined by x. So you can kind of think of, we have the group x, and this group x has some distribution, and then we introduce some intervention, like the spicy food, and this distribution is initially completely determined by x, and after the intervention it could either shift in location or can shift in variance a bit. The point is that the distribution of y is dependent on the distribution of x. And also, it's worth mentioning, these distributional assumptions do not have to be normal. You can generalize this to any parametric distribution. However, for the sake of comparing to the dependent t-test, which uses a normal distribution assumption, I will also be using a normal distribution, but that does not have to be the case. You could do this for an exponential distribution, for example. So now let's get into defining the test statistic. So when comparing means, it's natural to let our statistic be something very simple like mu x minus mu y, taking the difference. And these are the population values, and so of course if we want to translate them into the sample values, I'm just using x bar minus y bar, which is obviously the sample mean for both x and y. So under the null hypothesis, h0, we assume that these means are equal. And so now from here we can begin to start deriving the asymptotic distribution. And so first I start by deriving the expected value. And so we get the expected value of x bar minus y bar. And due to linearity of expectation, you can break this up into e of x bar minus e of y bar. And since these two are equal, this is 0. I mean, honestly, we didn't even have to break it out to see that, but I did it anyways. But under the assumption of the null hypothesis, x bar and y bar are 0, so the expectation is also 0. So that's pretty easy and straightforward. However, now we get to the very long part, which is deriving the variance, and the variance is very a little complicated. So we begin by defining the variance of x bar minus y bar, and I use the delta method here. I won't be covering the delta method in this video because 1, for the sake of time, and 2, I have already covered the delta method probably 2 or 3 times at this point. In fact, I think I have a video dedicated to the delta method, so if you are unfamiliar, I would highly recommend either reading about it on Wikipedia or seeing one of my older videos. But anyways, I'm using the delta method to derive the variance. And so using the delta method, we get the squared partial derivative with respect to x times the variance of x, plus the squared partial derivative with respect to y times the variance of y. And then we have the partial derivative of x then y times the covariance of x and y, plus pretty much the opposite, the partial derivative with respect to y then x times the covariance of y and x. And of course, you could probably notice that these two things are equivalent, and so I just reduce this to 2 times tx ty covariance. And of course, this is over n, which is our sample size. And so tx represents the partial derivative with respect to x, and so tx equals 1 because if you take the derivative of this with respect to x, this is 1. And then likewise, taking the partial derivative of this with respect to y is -1, which should be pretty obvious to see. So since x comes from a normal distribution, and it's our only non-dependent portion, we know the variance. The variance of a normal distribution is sigma squared, and so I have sigma x squared plus variance of y minus 2 times the covariance, whereas notice that the partial derivatives dropped because since this is 1 and this is -1, 1 squared is 1, -1 squared is 1, and 1 times -1 is -1. And so that's why you get this minus 2 times covariance here. And then of course 1 squared, both of those are 1. And so that all works out nicely. And so now we get into the first non-trivial piece, and that's deriving the variance of y, this portion right here. And so to derive the variance of y, I get the marginal distribution, and to get the marginal distribution, you have to integrate the joint distribution with respect to x. And so here I'm getting the joint distribution of x and y, which can be expressed as the probability of y given x times the probability of x. And so you can see that the mean of y is dependent on x here, because recall in our setup we denoted that the mean of y is completely determined by x. So this makes sense. Our mean for our y is x. And then right here, this is just the density of x. And so the distribution of x obviously has the mean mu x and standard deviation sigma x. And also notice that I have this sigma y here, it's important to note that this sigma y is not the standard deviation of y, but it's the standard deviation of the dependent portion of y. And so if you see the sigma y, do not confuse this with the variation of y itself. This is only the variation of this dependent portion of y, which is different. And so after we merge these, we get this constant term, which we can take out, and then we just integrate this with respect to x. And this integration is a bit long, and so I've omitted pretty much all of the steps here. You can either do it by hand using Gaussian integrals, or you can use an integral calculator, and you will come up with this result here. And you can see that if you are very familiar with the form of a Gaussian distribution, that this right here is the variance. And so the variance of y is sigma x squared plus sigma y squared. And so that's the difference here. So this sigma y is not the variance of y itself, because that's the sum of the two. The sigma y is only the variation of this dependent portion right here. So that's important to note a bit later. So anyways, after we get the variance of y by integrating out the marginal distribution, we got sigma x squared plus sigma x squared plus sigma y squared minus 2 times the covariance. So now the final tricky thing is to derive this covariance. And so here I've kind of just, I rewrote the joint distribution. So this is the joint distribution that we just had, our dependent portion, which has a mean which depends on x, and then our density of x. And so the covariance, statistically, is the expected value of xy minus the product of the expectations. And so notice that if x and y were independent, this would be 0, obviously, but they are not independent, and so we will have to derive this thing. So these integrals look scary at first, but I promise you they are pretty trivial actually. And so to get the expected value of xy, we take the double integral over both domains of x and y, and we take xy times our joint density, and then I'm doing with respect to y and then x. And so after we put in our joint distribution here, this is the constant term, and then this is just the remaining portion. And notice that we can take out this x density because we are integrating with respect to y first. And so we take out this x portion, and then notice that this is pretty much the mean of y, and the mean of y is just x. And so then we get x times this portion here, so now we get x squared times the e to the whatever, and now we are left with pretty much the second moment of this normal distribution. And the second moment of a normal distribution is sigma x squared plus mu x squared. So if that was a little confusing, I would recommend pausing it here and try to see that integrating this with a little bit of manipulation of this constant here. This is taking the expected value of a normal distribution, which is equal to mu, but in this case mu is actually x. So this x multiplies this portion here, which gives us x squared times the distribution of x, which is the second moment, and that gets us to here. Alright, so now we have exy minus ex times ey. So we got sigma x squared plus mu x squared minus mu x times mu y. However, under our null hypothesis, we're assuming both of these to be equal, which implies that this product is equal to mu x squared, and then we get mu x squared minus mu x squared, so that cancels out. And then we're left with just sigma x squared. So now, that's our covariance. And so then after plugging everything in, we got sigma x squared plus sigma x squared plus sigma y squared minus 2 times sigma x squared. And notice that the 2 sigma x squared cancels out with this positive 2 sigma x squared, basically. And then we're left with sigma y squared over n. And this is where it gets important to distinguish sigma y squared with the variance of y. Because recall that this sigma y squared is the variation of the dependent portion, not the variation of y. So that's pretty much the first bullet point here that I wrote. Notice that we don't actually have sigma y directly, only variance of x, which is the sigma x squared, and the variance of y, which is sigma x squared plus sigma y squared. And it may be tempting to approximate sigma y squared with just taking the difference, because notice if you take the difference, sigma x squared plus sigma y squared minus sigma x squared, then technically you would get sigma y squared. However, if the variance of y in your sample happens to be less than variance of x, then this can lead to pretty much undefined behavior or dangerous behavior. And before I recorded this, I did some simulations of that, and I ran into a lot of problems. And so this is a very bad approach. And so to avoid that nonsense, a more statistically sound way or statistically robust way to estimate sigma y squared is to just do the standard approach of maximum likelihood. So that's what we'll do next. So recall that y, our distribution of y, is this joint distribution here, which we've seen a couple of times already. And so now if we take n samples of y, then we can take the n joint distribution, which is basically taking the product of y n times for our n samples, and then we get this joint density here if we take the product n times. And notice that this right-hand side doesn't involve sigma y at all, and so we are not really concerned about it. And so then we can take the log likelihood to make the derivative a bit easier. And so this bottom portion here is after we take the logarithm of this piece. And notice that we can safely drop this term because if we take the logarithm of a product, then that turns into a sum of the logarithms. And so ignoring this piece is completely fine because after we take the partial derivative with respect to sigma y, this entire term is going to reduce to 0 anyways. So anyways, this is our log likelihood, and now we can take the derivative with respect to sigma y and actually get its estimation. So we want to maximize for sigma y squared, this expression here, which is the log likelihood. And so I won't be walking through in super detail this derivative. I think it's pretty straightforward. I would recommend pausing it just to kind of digest this information. But essentially, taking the derivative, we get this reciprocal, and we do a little bit of trivial algebra, a little bit of rearranging, and then we get probably what you would expect, where the variance is estimated by taking the yi minus xi squared over n. And technically this is a biased estimate because maximum likelihood estimation for variance is a bit biased, but in our case it's not really a big deal, to be honest. So the final form of our asymptotic variance is, and notice that we divide by n twice because our variance from a couple slides ago is sigma y squared over n, but sigma y squared itself is also over n. So we divide by n twice, which leads to n squared being in the denominator. So we got sigma y squared over n, and sigma y squared is this expression, which is also dividing by n. So we get the sum of yi minus xi squared over n squared, because we are dividing by n twice. And so now, finally, after all of that work, we can express the asymptotic distribution of our test statistic. And so we can get t of xy converges in distribution to mu x minus mu y as our mean. and the sum of yi minus xi squared over n squared, which is our variance. And of course, if you want the standard deviation, you would just take the square root of this. And using this, you can also derive the approximate 95% confidence intervals using the empirical rule that for a normal distribution, roughly 95% of the data is within 2 standard deviations. And so you can use mu x minus mu y minus 2 times the square root of our variance, and then likewise for the upper bound, except using plus. However, if you prefer to work with standard normal distributions, then you can normalize it by dividing by the variance. And so our expected value then becomes mu x minus mu y divided by the square root of our variance. And then after normalizing it, our variance obviously becomes 1. And then the confidence intervals, now that we've normalized it, become this normalized term minus 2, because now we have unit variance, so this is just 2 times 1. And then likewise for the upper bound. And that's essentially the complete derivation of an asymptotic approximation to the dependent t-test. So now if you've made it this far, I will go switch over to RStudio and we will do a couple of simulations. Let me just increase this font size a bit. Alright, hopefully you can see this a bit better now. So here what I'm doing is I'm generating some synthetic data to simulate the distribution of the test statistic. And so here I'm creating X, our X group, which has a mean of 2 and standard deviation of 5. And then our Y variable, which is our dependent variable, has a mean, which is dependent on X, and then it has its own variation. And so the standard deviation of 3 here represents the variation of the dependent component, not necessarily the variation of y itself. Keep that in mind. So this was the whole sigma y squared thing versus variance of y that I was talking about like 10 minutes ago. And so after generating the x and dependent y, our test statistic is just taking the difference in means, which is what I defined the statistic to be. And so I'm just generating this for 30 samples to start. So we can generate 30 samples. Now we can plot this. So this is what the distribution of the test statistic looks like for 30 samples. And then here, let's get the simulated standard deviation, which in this case is 0.54. And then using our asymptotic approximation, see this is, we're taking the sum of yi minus xi squared over n squared, which is 30 squared, and then the square root of that to get the standard deviation. And so our asymptotic approximation is 0.59, which is not terrible, but the reason why it's a bit bad is because the sample size is relatively small, and as you may know, asymptotic approximations really work well if you have a somewhat decent amount of data. So let's resimulate this for 100 samples. So doing it for 100 samples, you can see that the variance got a little bit tighter here. So taking the standard deviation, the simulated standard deviation, I got 0.298. And then using our asymptotic approximation, I forgot to change the sample size. I was a bit confused there. So we got 0.2955. And so these are pretty close. It's not bad. So for 100 samples, the variance estimation is pretty good. So now we'll go on to the more interesting thing. And I'm going to actually do the hypothesis test. And so you can see what I did here. I just put together this asymptotic test function, and this is essentially checking if 0 is in this confidence interval. And so on that last slide, I had the confidence intervals. And so I'm using the confidence interval approach to do a hypothesis test. And so here, like before, I'll start off with 30 samples. And then what we're doing is I'm generating that exact same data that we were just looking at. And then I'm doing a paired t-test, which is, I think, in the stats package. So this is like the quote-unquote official t-test. And then I'm using our asymptotic test, which is all of the math that we just derived. And I'm using a significance of 95%. And so here I am checking if it's below the 0.05 alpha. And then I'm simulating this 1,000 times, mainly because R is a little bit slow, so 1,000 is a decent speed. So now, I forgot to mention, we are testing against the null hypothesis right now, or the null hypothesis in this case is true, because this mean is exactly x, and so theoretically there really shouldn't be that much of a difference. And so this mean here, this represents the false positives, and so the null hypothesis in this case is actually true, but it rejected the null hypothesis about 5.8% of the time in this simulation. And for our asymptotic test, we got a pretty much exactly 5% false positive rate. And of course we can resimulate this. So going on the second simulation, the actual t-test had a 4% false positive rate, and then our asymptotic test had a 3.6% false positive rate. So it seems like it's pretty much in line if the null hypothesis is true. So how about the power now? So I'm shifting the mean by 1.5. So now the null hypothesis is no longer true. Our means are different now. And so we should see some differences. So now if I simulate this while the null hypothesis is false, using the t-test, we got a 77% true positive rate, because recall now the null hypothesis is actually false. And then using our asymptotic test, we got a 74.9% true positive rate. And note that these values are low because our sample size is low and also our variance is a little high. And so the statistical power in general for this case is not very good. However, let's go to something a bit more attractive. And let's do 300 samples, which should give us much more statistical power. So doing the same simulation for 300 samples, the t-test, we essentially got a perfect false positive rate, and then likewise for the asymptotic test. So both of them detected the difference in all 1,000 cases. But let's also just bring this down to 100 just to see. And so for 100 samples, we got a 99.9% true positive rate for the t-test. And then our approximation, we got the exact same thing. And for the sake of completion, let me make the null hypothesis true one more time for 100 samples. And the t-test false positive rate is 3.9, and then our approximation is 3.8. So they were extremely close. So that pretty much covers it. We derived an asymptotic approximation to the dependent t-test, which with enough samples is pretty much 1-to-1 almost. So hopefully you enjoyed that. Hopefully you learned something. And I guess I'll see you in my next video.